Is our planet reaching the point of no return? With global temperatures rising and natural disasters intensifying, this question is becoming ever more relevant. But is this question also being politicized? Dr. Steven Koonin is a theoretical physics professor and former undersecretary for science. In recent years, he's been criticized for his stance on climate change and efforts to separate the politics from the science. Join us to hear his take on what climate science tells us, what it doesn't, and why that matters. Welcome, everybody, to another exciting edition of the Into the Impossible podcast. It is I, your formerly fearful host, Dr. Brian Keating, joined with a very, very special guest today, all the way from New York City. It is Steven Koonin, a renowned physicist and more recently involved in government policy and also urban studies of a kind, and we're going to get into all that. Welcome to La Jolla.
Great to be here, Brian, and chatting with you.
We have so many things to talk about today. We're going to talk about your wonderful book, which is provocative, which is controversial, which is technical and chock full of information. We've had on many climate scientists and those who are interested in climate change, just from a human perspective. We recently had on Kim Stanley Robinson, who's written many books about this, who's an alum of UCSD, as it turns out. And we had on Tim Palmer last year, who shared the Nobel Prize, I believe, back in way back in the mid-2000s, along with Al Gore. And I think maybe we'll start with the book, as we often do, because when you see a book, you're never supposed to judge it by its cover. But my audience knows I love to judge books by the covers, because what else do you have to go on, when you don't know the author? I know you very well. Your reputation is titanic. Explain for my audience, please, the choice of title, the subtitle, and most delightfully, the art on the cover as well.
Art, right. Yes. So let me start with the title. And, in retrospect, I've come to understand it's really a triple entendre. It refers primarily to the state of the science, that there's an awful lot we don't know about climate science. Mm-hmm. It refers to how I felt and how many other people feel when they're exposed to what the UN, for example, or the research literature says about what we know and what we don't know. And then finally, it refers, I think, to the uncertainty about what we're going to do about all of this, the growing human influences on the climate. So that's the title, if you like. A major motivation for writing the book was to expose non-experts to what the IPCC, the UN Climate Panel, and the research literature really say about what we know and what we don't know, which is very different than what you get from the media or the politicians or other activists who are talking about climate. Mm-hmm. As far as the cover art goes, I know very little about that. I was given a set of possibilities. Pick one. I consulted with a lot of people, and this is the one we came up with.
I very much enjoyed this book. I listened to an audio. We have the physical hard copy, and discussing it in detail, I think, is necessary for an audience like mine. It is an erudite audience, the most intelligent audience in the known universe, I like to say. And I want to take it back, as I often do, to my hero Galileo. And Galileo said the following: our job as scientists, he said, is to measure what's measurable and to make measurable what is not yet so. And your late great colleague at Caltech, my former advisor and mentor, Andrew Lang, he quoted that on the occasion of the induction of him and his team into the Linnaean Society, which is what Galileo would put on all of his books after. What do you make of the ability of climate scientists to both utilize the methods of science, of hard science, of data acquisition and collection, a lot of which is done here at Scripps, but also to maybe make inroads into politics, as Galileo did, unintentionally so? What do you make of the highly politicized nature of this? Because I don't have this in cosmology. Nobody wakes up and says, I hate that constellation over there. That's a Republican constellation. I will not look at it. Why has it become so politicized? It is atmospheric chemistry, which is derived physics. Tell me, Steve,
there is a real science at the heart of all of this. It's actually a wonderful science that mixes up physics and biology and geology and chemistry and so on. And as I have learned it over the last 20 years, I've become a fan of it. I think it's great. And we can go into some of the challenges and so on. But I think what has caused it to come a cropper, if you like, or become so politicized, is that the implications of it, if some people are correct, mean that we need a radical restructuring of the way society works globally in order to reduce greenhouse gas emissions and find other ways of using energy. Many scientists in the business, though not by no means all, have come to mix up their role as informers and advisors with that of persuading and trying to dictate policy. And I think scientists cross the line when they do that.
Yeah, I call them political scientists.
All right, very good.
Now, one of the things that I very much enjoy about this book, and I emphasize quite frequently with controversial guests that come on, with those that don't believe, sort of quote unquote, on the standard narrative or the accepted narrative that is settled science, as obviously the book connotes dissension from that opinion. But the notion that we should listen to experts and that there is uniformity of experts, and even if there's a preponderance of experts, I mean the statement by this gentleman Albert Einstein that when 100 scientists came out against the theory of relativity, he said if they were really right, just need one.
Of course.
But of course we have people like your former colleague at Caltech, Richard Feynman, who would say things like science is the belief in the ignorance of experts.
Yeah.
So what do you make of this? What is a layperson to do, or maybe an educated layperson, technically minded layperson? We are dealing with a heat wave. They tell us of unrivaled proportions, and yet that wasn't predicted last year. In other words, we're living through supposedly the warmest year on record, maximum records in Palermo, Sicily, just yesterday, 25 days of heat over 110 degrees in neighboring Phoenix. What is an educated person to do when confronted by seemingly disparate facts and evidence, local and predictive? How do we assess all of this?
So I teach climate science at the graduate level at NYU, and I'll start teaching again in a month or two. And what I tell the students is, first of all, it's a mix actually of engineers and business people. I tell them, don't read the summaries, don't read the press, read either the IPCC summaries or go look at the data yourself, and then judge from that. And eyes get opened up when they read, for example, there are no long-term trends in hurricanes, as you can find in the IPCC report. A lot of confusion is about weather versus climate. The official definition of climate is that it's a 30-year average of weather properties. Averages, extremes, variances, and so on. And so anything that happens in one year or in a given year is not climate. So, for example, California has been in drought for the last 20 years or so. That's climate. But then you get last year a deluge of biblical proportions. That's weather, unless it continues for so many months, so many years. So, the tricky thing about all of this is that the weather has natural cycles in it. The El Nino is probably the most familiar cycle. But then there are longer-term cycles, periods of 60, 70 years, which are probably called climate cycles, such as the Pacific Decadal Oscillation, the Atlantic Multi-Decadal Oscillation, and so on. And you can get fooled. Right? I like to show, as you can find in the book, the record of the height of the Nile over almost 1,000 years, which the Egyptians were able to compile. And what you see is that there's tremendous variation from year to year, but there are multi-decadal trends. And so in the beginning of the record, starting at about 630 AD, you see it go down for about 100 years. And no doubt there's some medieval Egyptian climate panel saying new normal, as it got drier and drier. And if they just waited 100 years, it comes back up again. So this is one of the challenges in the science, to distinguish the natural variability from the response to human influences.
My particular interest will be on astrophysical constraints, and we'll get to those in a minute. But just to point out, I often go down to visit my friends that have a much nicer view on the coast of La Jolla Cove that are based at the Scripps Institution of Oceanography, which is co-recipients of that same 2006 Nobel Prize with Vice President Gore at the time. And there's a picture, and it shows the very first building, which comprised the very first academic institution in La Jolla, California. And that is the Scripps building, the director's building, or their office building. And in the background, you can see La Jolla Cove. And you see these our famous sea caves and whatnot. And you see Scripps Beach, which is a protective thing. And the sea level, and those are taken in 1905. The sea level hasn't changed at all. I mean, actually completely identically flat, no variation. And this is like, you can see the evidence right outside your window if you're down there. So to what extent should we pay attention when we hear things like, Florida, coastlines are going to be underwater, and Manhattan's going to be, you're going to be, kayaking to work next year in the village. To what extent should we be mindful of truly planetary scale phenomena, of which, sea level is a certainly very, very important metric. To what level can those be tied to physical observables that may be predictable?
Yeah. So the prediction is quite a separate matter. You start first by asking what has been changes at the global level or at regional level over the last 120 years or so, which is about as long as we've got good records, maybe 140 years or so. If you go back beyond that, you get into historical records, and then even further back, you've got paleo proxies, tree rings, lake vars, things of that sort. Okay, so we only have a relatively short record, and we do see changes on the multi-decadal scale in that relatively short record. I described for you the Egyptian height of the Nile, but global temperature has certainly gone up. We've gone up about 1.3 degrees since 1900, and that rise is not monotonic. It was rising pretty rapidly from 1910 to 1940, was flat or slightly declining from 1940 to 1970, and then has been going up again since about 1980. So that alone will tell a scientist or even a non-scientist that it's a lot more complicated than just CO2 was warming the planet, because the CO2 was increasing steadily during that time, but the temperature's going up and down.
Right. I mean, oftentimes I see things like, it's the highest temperature ever, set a temperature record last set in 1947. Well, then why was it ranging, or 1847? And that kind of brings up the notion of what we call, Malmquist bias, or a form of sample variance bias, that we're attentive to things that we can measure. As Galileo said, you should make measurable what you can't measure, and we don't have built-in CO2 detectors in our heads. So by making it measurable, what extent is correlation conflated with causation?
So the IPCC, when you read the reports as opposed to the summaries, very carefully distinguishes between the detection of a change, which is relatively straightforward if you've got the data, versus the attribution of a change to human influences, let's say rising greenhouse gases. That attribution is really tough for two reasons, at least. Maybe I'll think of a third, but I've got two at least. One is it's a very noisy system, as we've said. The second is that there are these natural long-term oscillations as opposed to the forced response. And then the third is that human influences are physically small. The planet absorbs and re-radiates as heat about 240 watts per square meter of sunlight that comes back out as long-wave infrared radiation. The human influences on that net of CO2 and aerosols and methane and nitrous oxide and so on is about 2.5 watts per square meter. So we're talking about a 1% change in the radiative balance of the planet. And you might say, well, that's not a big deal. On the other hand, if you do astrophysical style estimates, 1% of 300 Kelvin is 3 degrees. And so the numbers are about right. We worry about 3 degrees. But it's a small number, which means you're in the noise as far as other influences go.
And often we see these plots, the famous Keating curve, of course, derived here by Keating,
Right.
Professor
I
Keating.
knew Chuck Keating. Yes,
Oh, you did?
I
Oh,
did.
wow,
I did.
fantastic.
Yeah.
So his, I want to get into him and his son, who's currently a professor
Yeah,
here,
yeah,
because I've heard wonderful talks by him that are persuasive, and I think it's very interesting to get into these discussions. Let's first take a giant leap backwards. Let's talk about you're a theoretical physicist by training. What is a model, and how does it differ? We talk about the standard model of particle physics. We talk about models of cosmology that I study in my graduate students. What is a model, and then by what metrics can we really apprise the goodness of fit of a model? In other words, we talk about sigmas, and we're getting into lots of sigmas. And what is a sigma? What is a model?
A sigma is a measure of uncertainty, either in the data. No measurement is perfect. There's always some range of likelihood for a given measurement. And then the models, there's not just one climate model. There are about 50 of them, and they don't all give the same answer. And so you can have a sigma or uncertainty in the model as well. And so we're trying to compare two uncertain quantities. How did the climate change over the last 80 years, and how do the models predict or describe that change over the last 80 years? Because, all right, so let's talk about what a model is. In the present context, it's a large computer program that follows the motion of air, water, momentum, energy, radiation through the atmosphere and in the ocean, where you also have salinity and currents, step by step through of order 10 million voxels for 100 years, and tries to describe the gross features of the climate system: jet stream, Gulf Stream, deserts, Hadley cells, things of that sort. And then it tries to say, if the CO2 goes up, how are things going to change? So that 1% change in the radiative balance. And that's a very difficult problem to do, in part because it's a big computer problem, but more importantly, the size of the boxes you can make in the model is only about 100 kilometers on a side. All right? And there's a lot that happens within a box. Think about thunderheads, for example, which are a few kilometers long. You can't describe those explicitly, and so you're going to have to make an assumption about how many clouds are there, where are they in the voxel, when do they appear, when do they disappear, because that affects the sunlight and the infrared radiation. Different people make different assumptions, and so you get different answers.
Behind you is a vial. There's a large beaker, and that I collected when I was at the South Pole in Antarctica. The second time. I've been there twice on occasion of the national government sending me there on a all expenses trip for the bicep experiment. There's cosmology, tremendous work that's done there, including samples of ice cores that go back hundreds of thousands of years and monitor the science of climate, CO2 impact. Goes back to Arrhenius and others back in 1800. They started
to realize the infrared activity, and then, hey, this is going to change the climate. They thought it would be a good thing.
That's right.
Arrhenius was from Sweden, maybe not surprising.
That's right. And Nobel are preferentially biased towards Swedes. So when I look at that vial now, I'm reminded of some recent talking points that I'm seeing online, that we have a 6 sigma deviation to the negative of Antarctic ice shelf thickness as measured by, or extent rather, as measured by these satellites that do such things. And it's just obvious when you see the trend, and I'll put a picture up on the for the viewers and listeners to the podcast on audio can find it on my YouTube channel, Dr. Brian Keating. But if you can speak to that, what level of concern should we have when you see a number like 6 sigma? It was good enough for Higgs to win a Nobel Prize, right? So what do we make of this? As a theoretical physicist, you'd be delighted if any of your predictions were 3 sigma.
The problem is that today's 6 sigma happened many times in the past. Okay, so particularly with respect to ice, and we can maybe talk more interestingly about the North Pole at some point. But things change a lot. The planet currently is coming out of, well, we're not sure what it's coming out of, but it's in what's called an interglacial. If you go back 20,000 years, the planet was mostly covered with, well, not mostly, but there was a lot of ice on the planet, and the great ice sheets extended down to Chicago or even New York. And if you go back even further, 125,000 years ago, those ice sheets had retreated. Basically, they were less than what we have today, the planet was a degree warmer, and sea level was 6 meters higher than it was. That's called the Eemian period. All right, and those variations, which are pretty cyclical, are driven by astronomical phenomena, the way in which sunlight falls on the Earth's orbit, the tilt of its axis, and so on. So we shouldn't, at one level, be real surprised that we're losing ice right now.
In terms of returning to astronomical topics, my favorite subject, besides me, is the net amount of carbon is not infinite. There's a certain amount of biological material which was deposited, millions or perhaps even longer, hundreds of millions of years ago, and even according to anyone who is firmly believing in the anthropogenic and carbon dioxide modulated global warming, they will say, under oath, they will say, yes, there's a limit to how much carbon we can't produce. Where there is not an infinite store of carbon in the Earth's crust, and we don't have access to it. To that extent, what are the kind of astronomical or planetary scale phenomena? It's been calculated. I heard Charles David Keeling was the son of Ralph Keeling, right? And he spoke about this. He first brought it to my attention that there is a finite amount. So to what extent do we have to worry about reaching the complete combustion of that carbon, converting to carbon dioxide, before, say, we reach what I call, clean energy escape velocity? In other words, at some point we will have fusion. We're going to talk about that. We're going to talk about fusion. We're going to talk about high TC superconductors because I can't resist with a physicist. I love to nerd out, and we will, and it's very pertinent to this climate discussion. Right. But to what extent can we make it kind of stretch the glide where we're never going to burn all that carbon? But even if we did, there's some upper limit on how much we're going to burn before we hit escape velocity, and just everything except for rockets are clean.
So this is where the real world of economics and technology, people in the fossil fuel business, which is what carbon is in the ground, oil, gas, and coal, talk about a supply curve, namely how much oil or gas or coal could I get out of the ground at today's price with today's technology? And the answer is we've got known carbon in the ground, known in the sense that you could invest in it. We've got about 30 or 40 years of oil, let's say. And you might say, oh my God, we're going to run out. But in fact, what's called the resource as opposed to the reserve, the amount of stuff you could imagine getting out with better technology or at a higher price, that's 100 years at least, okay? So we're not running out anytime soon, but it may be that the cost of extracting it will go up, and at some point it becomes more economical to get your energy some other way. Right? So we will not run out. But as the famous quote that the Stone Age didn't end because we ran out of stones.
Right.
All right. The carbon in the ground is so much more than what we use right now that's not going to be a major factor.
So you brought up, fossil fuel companies. I'd be remiss to say that you didn't, participate and you weren't involved with British Petroleum for some years. And, what do you say to those people out there, like your fellow professor at NYU, Professor Scott Galloway, who's in the Stern School? He said, quote, "Science is uniformly on board with the climate, almost what you might call, extremist, and only the right-wing lunatics deny that this is settled."
Right.
So what do you say to Scott?
Yeah, so what I would say to Scott is, if you've read my book, Scott, you'll see that everything I say is right out of the UN reports or the research literature. And so if you think I'm denying something, tell me what I'm denying, because I'm quoting to you the official science. Scott, your problem is you haven't read the reports in any detail.
That's right. So, getting back to the question of human innovation, and when we're using different types of stones, glass and metal and so forth, silicon stones, right? Petrochemicals, right. So I always say, that when people, and lately there's been a tremendous amount of interest in extraterrestrial life, and it's a fascinating topic, and we do talk about this quite a bit on this channel. Right. But besides that, I always wonder, for a spacecraft to get here, I claim if we were going to go spacefaring and they were to ask us when we get to, planet Blorcon 7, they would ask us, oh, how'd you get here? What was your technological pathway? And at some point we'd have to describe what a whale is, right? I mean, there's no way. Like solar panels don't come from solar panels. We didn't build a microprocessor using microprocessors. So we had all this primitive technology. So my question is, how likely is it that another civilization exists that has fossil fuels, has some form of prebiotic or advanced life forms, and that was then used over geologic timescales, maybe involving plate tectonics, etc. But how likely are these planetary phenomena ubiquitous throughout the universe is a question I've always had.
So the laws of physics, we believe, are invariant.
That's right. I hope so.
Including the laws of chemistry.
That's right.
Which are much more rich than the physics laws. But anyway, there's only a finite number of ways to get energy out of the universe. You got radiation, photons, you've got the rearrangement of atoms, you've got the rearrangement of protons and neutrons, you've got gravity, and we pretty well have tapped into all of those in one way or the other. So I would be very surprised if we came on a civilization that had yet another way of getting energy out.
Yeah. And because it's a precursor, you can't build a fusion reactor unless at some point you had fossil fuels, at least in our timeline. Yeah, I've talked with Professor Adam Frank of University of Rochester about this, and he's claimed that we should look for, as a techno-signature, we should look for global warming on another planet. We should look for CO2.
Wow. Okay, it's really hard to be able to do that, all right? We have a hard enough time measuring the temperature of our own planet. All right?
Well, maybe not global warming, but carbon dioxide.
Well, sure, there will be carbon. Of course, we know
oxygen,
that there's carbon left over. From
molecular oxygen, things like that. Is it true that there are much more powerful sources of atmospheric forcing functions like methane, water vapor as a greenhouse gas? At what level do you think that these people who are so in the climate, kind of leading to catastrophe caused by human beings, settled science, so-called camp, how do you respond to them when they seem to have multiple agendas? Like one agenda that I'm hearing a lot is what I call, or what just seems to be like kind of anti-natalism, where they want to have population control. And this is very reminiscent of, the 1970s when this was Ehrlich and others on the East Coast.
I remember. Yes.
They were complaining about
Rome and all that.
Yeah, who won all these prizes, of course, and depopulation seems almost like a more pressing concern. So some of the concerns that I've heard about this book, or complaints about the book, is that, look, you say things, there's some fixed fraction of the Earth's population who are going to die, whatever that means, are going to be killed by, again, this is their terminology.
I didn't say that.
No, you don't say that, but you make a forecast, or there are forecasts in the book, and people make this, how many deaths can be attributed to global warming. So can you speak about that?
Let's talk about the deaths, which I talk a little bit about in the book. Let's talk about what has been first rather than what the projections are. And there's actually now I think 2 articles in The Lancet, which is a reputable medical journal, which looks at globally the deaths attributable to temperature extremes over the last 20 years. And what they find, and I've referenced the paper in many talks I've given, it's right there, anybody can look at it, is, and I'll make up the numbers approximately because I don't remember them exactly, about 5 million deaths from 2001 to 2018, globally 5 million, were attributable to temperature extremes. Of those 5 million, 90% were attributable to extreme cold, and 10% were attributable to extreme warmth.
Right, but there's no way to target. Let's just have some warmth targeted to Minsk. Where these deaths are taking place. Right.
No, I mean, but to say that the warming of the globe is causing more people to die, is a true statement.
Right.
But it's not factually complete.
It's not,
because it's also causing fewer people to die from cold. And the net actually is that there are more people alive because the globe has been warming.
What do you say to people, young people? I don't know if you have children, but I do. And I hear a lot about the following, that we should, actually the best way to reduce, the most effective way is not reducing the number of flights, not reducing the amount of meat that you eat, not, driving less and carpooling more, buying an electric car. It's having fewer kids. And I always get concerned about that, because I think there's a not, significant gap between that and saying, well, if more people died, it would be better for the climate, or if, climate suicides. And there are deaths of despair now, and there's tremendous psychological damage occurring to children because of climate, some call it hysteria. So how do you react to that? Depopulation.
Say to your kids again, I don't know them, but what I've taught my kids, who are 30 some odd years old, is that there are only 1.5 billion of us in the developed world, the OECD countries. All right, we live a wonderful lifestyle on average. There are 6.5 billion people on the planet whose theme or meme is not enough. Not enough energy, not enough food, not enough transportation, and so on. And it is immoral to deny them the energy that they need in order to live a better life. And so I would say to your kids, go spend some time in Nigeria or in the poor parts of South America, and then tell me that we should be cutting back globally on energy.
Yeah. Okay, so in the book you make a very interesting set of logical, syllogisms. One is that, in order for this to truly be catastrophic, it has to be caused by human beings. It has to be, unavoidable, irreversible, and so forth. So there are several different premises of the book, which seem, prima facie inarguable. Like, if humans aren't contributing to it, then humans can't necessarily solve it unless we, kill every cow.
Adaptation is a solution.
I want to get to that. So one theme that I believe is attributable to in the book is that there's no plausible way to reduce the CO2 contributions to the atmosphere. Now, I want to just, before you respond, I want to say, if that is your contention, what if I tell you that there have been two recent breakthroughs, one of which I talked about with your colleague Charles Seif, NYU, and that's nuclear fusion, and then today's news, which I've talked about with my colleague Jorge Hirsch here many times, and that is high TC superconductor. Let me tell you, God hands you a letter, says, Steve, guess what? I've got good news and I've got good news. We've got high TC, superconductivity, ambient pressure, and we've also got nuclear fusion, and they're about 6 years away. And better yet, AI is going to control everything, and so put AI in charge. Do you stand by that we can't vacuum out or decarbonize the atmosphere?
Look, if I had wings, I could fly, right? Okay. The thing is, I think there are two things here. Does the science or the technology exist? Okay, and we can talk about ITC or fusion. But the second is, it's got to be better than the alternatives economically and ability to scale. We can produce electricity right now from fusion. It's just a question of how expensive is it going to be, and will it scale? Right? Same is true of fission, by the way. It's a little more expensive.
Yeah.
But, if you're willing to pay the cost, you can run the whole country or the whole world on wind and solar. But that would take so much resource away from other things we need that it's a values question for the world. Do you want to do that versus giving more refrigeration to a few billion people?
Pivoting off of that, my question wasn't only directed towards the supply side of the carbon equation. It was also the negative subtraction. And in other words, if you had infinite free energy on tap, could you suck out? And how would you do it? Have you thought about it?
Let's talk about the carbon cycle for a second. Okay, every year there are about 200 gigatons of carbon that flow up and back from the surface of the planet into the atmosphere and then back again. That 200 gigatons is caused by the growth of vegetation, it's caused by absorption or desorption in the ocean, and so on. And it's just about in equilibrium, we believe. Or at least it would be, except for the fact that we're taking about 9 gigatons a year of carbon and adding it to this annual cycle. So if you could make a small perturbation in that annual cycle by making plants grow better, for example, you could counteract some of the emissions, maybe all of it. So that's one, and people are trying to find fast-growing plants and so on. The other way of doing it is to capture it thermochemically out of the air, direct air capture, as it's called. There again, it's a question of economics and scale. The current cost right now is a couple $100 a ton of CO2 removed. And we're talking about gigatons. And so you quickly get up to big numbers. Now, yes, you should work on technology and so on, but it's not there yet.
I wonder if you have a take on the, if you can perhaps react from a physics level, the resistance to fission. I view that as a tell, because you'll see people like the famous, know-it-all Greta Thunberg talking about, well, no, nuclear can't be part of the solution. And to me and others, that's kind of like, you're drowning in the ocean. If you really think you're drowning, the old joke, you don't wait for the helicopter. God says, I sent you a helicopter, I sent you a boat. I said, but what do you make of the resistance to fission? I mean, is it all just like 3 Mile Island, Chernobyl, and Fukushima, or is there something deeper at work?
So there is.
We shut down the reactors. You probably saw on your drive down.
You shut down San Onofre. We shut down Indian Point.
It's $2 million a day to store the waste. So what do you make of this?
So. There's a very nice book by Spencer Weir, who is a historian of science, and I think it's probably about 40 years old, called Nuclear Fear. And it talks about the deep psychological fear that many people have of powerful forces that are invisible and you shouldn't be messing with. And he takes it all the way back to the Frankenstein myth, right? Do not reanimate, and so on. And I think a lot of people, that's a fear. All right. I think also there's personal fear, radiation. I don't understand it. There are issues, I think, soluble of what do we do with the spent fuel, not waste, spent fuel. But there are people who are starting to understand the realities of energy. Schellenberger, Stuart Brand have come out and said, we have to do fission.
I mean, it's the only one that's planetary scale. We could actually power incredible cities, and
20% of U.S. electricity already, and we
more
haven't
in France.
Built more in France. It's 80% roughly, or 70 something. We haven't built a reactor in this country in a long time. We just got a couple of new ones coming online right now. I think the technical innovation that's needed there is twofold. We need to be making reactors smaller. A typical reactor size is about 1,100 megawatts. People are talking about reactors that are 100 megawatt scale, so that's kind of the scale in a naval vessel. Build them in a factory, standard design, not like the big ones, which are each bespoke. And then the economics will be a lot better. But, it really depends. How much do you value being carbon-free? All right? If you don't want to be carbon-free, you probably don't need it. But if you care about carbon emissions, then it's absolutely essential.
We take a little detour here. I am very close friends with a person we have in common, Paul Steinhardt, who's also been on the podcast. And Paul has been accused of being a multiverse denier. I reacted to a book that makes such a claim. It talks about and not by a professional physicist. It talks about all the evidence for the multiverse. I'm blanking on the name, although I did review it for Physics Today about 3 years ago. So, but it didn't leave the greatest impression on me. But he talks about multiverse deniers. I found that in my review, I said that it evokes, kind of a word which should not have its currency devalued, not just because of my personal connection to, people that perished in the Holocaust, but there is a very consistent thread of people that accuse you of being, a climate change denier. What does that mean, and how do you react to that?
Yeah, I think it means that I don't buy into the narrative, which you can say in a few words, right? That we've already broken the climate and it's going to get a lot worse unless we do something rapidly and on a large scale. And I think when you read the science, so as I mentioned, what's in the book is not my science.
Right.
It's right out of the official UN science. So please tell me, what am I denying?
I guess what I've heard it criticized in particular was that the data are not. It's not saying it's cherry picked. It will say you took an AR or these assessment reports, right? AR5. So, but then AR6 came along and it showed that actually there's not. It went from low confidence to mild confidence. So how do you react to that? It's always going to change.
Okay,
right?
so it's always going to change. The book was written before AR5 came out, so I quoted AR5. I make in the book, references to some of the research literature that was included in AR6, and I'm pleased to say they say more or less the same things I said. There's probably, in the works an update, but there are essentially no things in there that I would change. Yes, some of the specific wording is different in AR6, but the fact that there's no long-term trend in hurricanes, that Greenland is melting today no more rapidly than it was 80 or 90 years ago, that sea level rise remains on a long-term basis at 3 millimeters a year. I mean, those are things that were in AR5, and they're there in AR6.
So one of your former students, apparently, Mark Boslow, wrote a review, which I felt was a series of straw men and women, maybe, that get torched. So it says, unfortunately, Unsettled is a book you can accurately judge by its cover. Well, thank you, Mr. Boslow, Dr. Boslow, maybe, because, that's my signature stock and trade as we open the episode. He accuses you of an all straw man concocted by opponents of the climate science in the 1990s, creating an illusion of arrogant scientists, biased media, and lying politicians. The phrase "science is settled" is repeated as target phrase. It seems like he only read the title. Bogus science is settled rhetoric. So he's really just taking into account the title and the and essentially the this notion that these things are constantly in doubt and never in doubt and always in error, as Landau used to say about cosmologists. Searches do come up with, but there are many examples of physical problems that are difficult to model. So a lot of the criticism I heard from Lawrence Krauss, who's been a guest on the show. He wrote a book on climate change. Tim Palmer, we're going to get to him in just a bit. Some of the criticism I get is Steven thinks he's better at modeling than we are, or he thinks that we are not as good as the modeling that is necessary and sufficient. How do you react to those criticisms?
Well, the modeling is what it is, all right? And again, I quote what's in the book. Let me say a word about Mr. Boslow first, or Dr. Boslow. He was in one of my classes, if I remember right. I don't think he was ever actually a student in the sense that
No, not a graduate student, right? But he tosses that in.
And of course. And the review he wrote, unfortunately, was really light on science. I mean, I'm happy to respond to specific criticisms. Koonin says X, but in fact it's Y. And you will find on my Medium page some really detailed responses to some of the mainstream climate scientists who criticized me, and I think I've responded effectively. Do I know more about modeling than those guys? No, absolutely not. They know more. But I do know modeling, all right? And I do know in other spheres what a good model is and what isn't, and also what the certainties and uncertainties are. And again, I just repeat what's in the book.
The last and most kind of ludicrous claim in this article by Mr. Dr. Boslow is the third is climate scientists, not deniers, that have been compared to Nazis and perpetrators of genocide. In fact, it was Michael Crichton himself, in the appendix to his book State of Fear, who directly equate, and I don't know, climate scientists to eugenicists. But wait, it is true. There is climate hysteria that is leading people to not have children, to not get married, and to consider having, becoming, sterilizing themselves so that they don't have children. So, I mean, maybe it's not eugenics in the Nazi sense, God forbid, but at a certain level, he's saying that you are in the camp that is accusing the good guys.
I'm not accusing anybody of anything at the science level.
Right.
I am accusing some of the prominent scientists, the journalists, the politicians, and some of the scientific institutions of misrepresenting what's in the official reports or the research literature. And I give in the book, and I've given subsequently, many examples of that, which are really tough to deny.
So the Scientific American also, which is no longer a real state of affairs that it used to be when I was a kid.
I loved it.
I loved it. I had the amateur scientist. I used to build the experiments.
Martin Gardner,
the mathematician. I loved it. I love that. That's really fallen out of favor. Yeah. But their critique is that the two such statements by Koonin follow the simple preamble for the literature and government reports summarized and say heat waves in the U.S. are now no more common than they were in 1900. That's one thing they're taking issue with. And the warmest temperatures in the U.S. have not risen the past 50 years. These are just data points, right? So it should be.
That. You can find it on the government
It's not
websites.
Your personal data, right?
Well, no, it's not my personal data. It's just the EPA. I can give you the URL. You can see the graph yourself.
And both of them, I have to say, Steve, the low level of intellectual kind of engagement of both of these things. The first one by Boslow's is predicated on the cover and the name of the book, and this one is predicated on the first 2 pages of the book. Yeah, it's clear. Look, I try to read every book or listen to every book, but certainly something I'm going to be talking about with the author. But certainly, if I'm criticizing a book, say the book about multiverse
you would think that both the Scientific American article and a fact check that was done by Climate Feedback, I think, they were criticisms not of the book, but of a review of the book. All right? And so the Scientific American folks put words in my mouth that are never in the book at all. And yes, I think the most disappointing part of all of this is that we have colleagues who are nominally accomplished scientists who are behaving in ways that we'd probably throw our students out if they behaved that way.
Let's go back to models. So the past 3 years have seen an incredible amount of both trust in scientific institutions and great skepticism, more or less predicated on the veracity of modeling. And I think, in the case of Tim Palmer, who's been a past guest and delightful to talk about, but he has called for, is in agreement with you, that we need better models. And I think he talks about the state. You talked about the size of these voxels, which are the three-dimensional analog of a pixel, which is two-dimensional, and getting those down to kilometer scale. So his words, that requires a CERN, our Manhattan Project style effort, which is nowhere in sight, and would seem to then require, government scale investment. What do you make of a CERN for climate change? How do you react to his?
The world is spending a lot of money on climate modeling already. I think it's misspending a lot of it because they spend cycles on doing silly runs for the IPCC about different emission scenarios. Let's talk about computational requirements first, okay? So naively, you would think that, you need 20, 30 layers up in the atmosphere and another 15 down in the ocean. But it's the horizontal size of the voxels that really determines the computational load. It's currently 100 kilometers. If you shrunk it to 1 kilometer, that's a factor of 100 linearly, a factor of 10 to the fourth quadratically, but then you get another factor of 100 because you got to make the time steps a lot smaller from the current condition. So we're now talking about a factor of 1,000,000. All right? It goes as the cube,
the
basically.
cube of that, right?
All right, and you're going to wait a long time before you got a computer that's 1,000,000 times more powerful than the exascale machines that are at the forefront today. So I think computing is going to develop for its own reasons. National security reasons in the U.S. and other things. And we don't need the climate problem to push that. I think you want better observations at the subgrid scale level. I think you want more continuous global observations, different variables. I think you need to engage professional statisticians, which they've not been doing right now, and you need more thinking than computing. Kerry Emanuel, who's another mainstream distinguished climate scientist at MIT, who was happy, by the way, to criticize my book before he read it, as he told me. Kerry says more thinking and less computing, or at least more thinking, not necessarily more computing.
More pencil and paper.
I agree.
Silicon.
Yeah, right. Understanding.
All right. I have a very long question, but since he is a past guest and a friend of the podcast, Tim Palmer. who authored a wonderful book. We had him on the podcast last year. You can find that. I'll put a link somewhere up here. He says the following. It's a lengthy question, but here we go.
Go ahead.
Climate models are not perfect by a long way, and collectively they do not tell us how bad climate change will be in unambiguous terms. At one end of the spectrum, they predict climate change outcomes which could well be manageable by society without substantial mitigation.
Right.
At the other end, they predict outcomes which are catastrophic, indeed existential to much of society, e.g., through semi-continuous heat waves of a severity that the human body cannot withstand unless we do mitigate. The distribution of the possible climate changes peaks somewhere between these two extrema. And so we end up with probabilistic estimates of climate change. But we are getting used to probabilities in weather prediction. If the chance of rain is 20% this afternoon, will I bring my waterproofs, my umbrella in our afternoon hike? If I do, it will weigh down my backpack, making it somewhat uncomfortable. If I don't and I get drenched, it'll be extremely uncomfortable. So what to do? It's a personal decision, not one that a meteorologist can make. Given these estimates that are probabilistic of climate change, what is your opinion on whether it is worth the economic cost of trying to reach net zero by 2050, like the weather forecast? It's not a decision the climate scientists can make on behalf of individual society. So for all of your concern about skillfulness and realism of models, how have you decided? In his view, is the current estimated risk of catastrophic climate change big enough to get to net zero by 2050? I guess the one way to say it is there's an expected value, right? You took the probability of the negative outcome, the probability and the impact economically, human, impact, all sorts of different impacts, and then you subtract the negative of those possibilities. So tell me, how have you decided? Is the risk, is the Pascal's wager of climate change, I guess?
And what I would say is Tim is confusing his role as a scientist with his role as a citizen. Okay, I think his role as a scientist and mine is to properly portray the probability distribution to the decision makers. That's the broad society, industry, politicians, and not just in the U.S. or in the UK, but for the developing world, okay? And what we have to do is to balance the risks, uncertainties, and benefits of a changing climate against the growing need of the rest of the world for reliable, affordable, and clean energy. And in weighing that balance, it's a values discussion, it's risk tolerance, intergenerational equity, and oh, by the way, it's economics. If Tim were to ask that question to a general person in Nigeria, he will get a very different answer because those folks are facing a real existential threat that is certain, immediate, and soluble. Whereas the rest of us, it's vague, uncertain, probabilistic, and so on. There's a wonderful paper I like to quote by a guy named Anthony Downs. And he was a political scientist, economist, died a year or two ago. He was working at Brookings. But early in his career, he was working at UCLA. And in the 60s, he was watching the smog get worse and worse in the LA basin. And it was getting worse in large part because more and more people were getting cars. And what he said in this wonderful paper he wrote was that the elite's environmental deterioration is just the common man trying to improve his lot. And so, Tim, you go ask that question in Nigeria, okay? And let's get 100 different voices from 100 countries together and decide what we're going to do about this. Nobody has given an answer that provides the energy needs for the developing world and at the same time gets to net zero by 2050.
Right, and so we have to, think carefully about these things that are multi-coupled, and I guess that may answer the original question that I had: is why is this so fraught and perilous politically? We look up at a constellation, and unless we're looking at a comet or an asteroid coming to destroy the Earth, it doesn't involve existential questions. It may involve deeper meaning, philosophical questions, etc. So, okay, great. Well, Steve, we've reached the final segment of the podcast, where I love to ask my esteemed guests, such as yourself, 4 existential questions, which I call the final 4, or the quintessential quattro. No, I can't say quintessential when it's 4 things.
Right.
So the first thing, and all of them are somewhat related to Sir Arthur C. Clarke, who is the namesake of the center that I associatively direct here at UC San Diego, Arthur C. Clarke Center for Human Imagination.
Right.
And the first one has to do with his very, very famous quip, which is that any sufficiently advanced technology is indistinguishable from magic. And my super producer, Stuart Volkow, who's over there, hi Stu, always inserts that in every podcast opening. So you actually hear Sir Arthur's voice saying those iconic words. I want to ask you, in sort of a big picture, nothing related to the book anymore, what invention or creation of humanity is most closely evocative of magic?
You know, I often, my father died at a relatively young age, about 45 years ago. I often think what he would think if he were alive today to see the tools we have. Certainly information technologies that we have would have seemed magic to him, I think. And, you know, my other favorite is the biology. The advances that we've made in understanding and manipulating how living things work, those are, I would assert, indistinguishable from magic to people from as recently as 50 years ago.
In the spirit of Sir Arthur C. Clarke, the next question I like to ask is the following. He said, and I quote, "The only way to determine the limits of the possible is to go beyond them into the impossible," and that's the name of this podcast. I want to ask you what former event, in the form of advice to your younger self, maybe 20-year-old Steve, what would you advise him? You have 30 seconds to talk to old Steve or young Steve. What would you advise him to give him sort of the courage to do as you've done, bucking, you know, so many scientists around the world and with facts and data, to go into the impossible? In other words, advice to your former self. You got a few seconds to talk to your 20-year-old version.
Steve, you know, first of all, don't feel inhibited by self-doubt, by lack of self-confidence. You're no different than everybody else. You will make mistakes, but you'll learn from those mistakes. Use your imagination, but also use the tools that you've been given of logic, quantitative, love for understanding how the world works, and go out and just have a swing at it.
Okay, the next question is a quip by Sir Arthur. He said, "For every expert, there's an equal and opposite expert." And we talked about Feynman's quote that science is the belief in the ignorance of experts. What is an expert? Should we aspire to be an expert? These two gentlemen are kind of casting aspersions on this. When I used to think, and I still do, to be honest with you, that you should aspire to greatness. You should aspire to mastery and merit and earning. But how do you react to that? What do we make of these? You know, as William F. Buckley Jr. used to say about the he'd rather be governed by the first 100 names in the Boston phone book. So what do you make of experts? Do we need them? Are they
so let's
necessary?
Distinguish between experts in the sciences versus experts in other fields.
Absolutely, yeah, please.
And I think there are 2 dimensions of expertise. One is a deep knowledge of the subject, the facts, the figures, what has been done before, and so on. But then there's another dimension which is, I think, a bit pernicious, and that is that you get locked into certain ways of thinking, community ways. You know, plate tectonics is maybe the best example of where the experts were all wrong and the evidence was staring them in the face, but it took a long time until they came around. So, you know, respect expertise for their knowledge of the facts and figures, but not necessarily of the paradigm that they lay on top of the science.
Very good. Okay, the last question, inspired by Sir Arthur C. Clarke, is the following. He said, and I quote, "When an elderly," I'm not calling you elderly, but an elderly but distinguished scientist says something is possible, he is quite likely to be right. However, when he says something is impossible, he is very likely to be wrong. What have you been wrong about?
Oh, boy. I was wrong about the solar neutrino problem, okay, which
let's talk about that.
There was this famous factor of 1/3 deficit. And I think I've actually said at a conference at some point, there's probably some feature of the sun or plasma physics that was wrong. And I was actually sitting on a thesis at Caltech where it was about coherent neutrino propagation, and he came so close to what we now know is the answer. I poo-pooed it, said that can't be right. So I was wrong, okay? But, look, I would say a batting average of 1/3 on, like in baseball, on major questions like that would be doing pretty well. So I've been right about something.
They say, a theorist only has to be right once in his life to have a good career. An experimentalist only can be wrong once in his career.
Right.
Professor Steve Koonin, let me just take one quick question detour. What is the state of academia today? What's it like at NYU? NYU is I see it as a very imaginative. I've talked to people at NYU Abu Dhabi. I know there's one in Shanghai or someplace like that. Talk about academia. What does the new model of academia look like, and what can we do because you're a renowned teacher as well. Most of education is sclerotically stuck in the way it was in the University of Bologna in 1080 AD. Talk about what innovations we might expect from the perspective of a master teacher.
Yeah, so I'd like to distinguish the undergraduates from the graduates.
Of course.
I think at the undergraduate level, you've got to become an expert in something, at least if you're going to be in the sciences. T-shaped, so you got to learn your mathematics, you got to learn biology, geology, whatever it is you're going to specialize in, because that's the pedestal on which you can then reach out as a graduate student to try to tackle some of these broader multidisciplinary problems. I mean, in my own career, I cut my teeth in nuclear physics, and it took me about 15 years after my PhD to start to get interested in these squirmier scientific problems, never mind the societal problems. So I'd like to teach the kids at the undergraduate level, tend to the basics first, get some sense that there are these bigger problems, but don't try to tackle something bigger until you've demonstrated mastery of something first. But then at the graduate level, tackle those big problems. Absolutely.
Yeah, I used to say to my students, if I was your art teacher, I'd say paint the masters. Do the derivations that came before.
Exercises, right?
It gives a direct pathway to the. So when I was a kid, when I was thinking about graduate school, I said, they told me don't go into nuclear physics; it's a dead field. Now we've got Oppenheimer. You guys are rock stars, literally. Have you seen the movie yet?
Not yet.
Okay, you should see it.
Everybody's interested, right?
Yeah, everyone's interested. So. As someone who also served in the Obama administration, worked in government, what do you say about people, scientists and informing people in Congress, perhaps? You see the tragedy that occurred to him and the persecution that he underwent. You've been relentlessly attacked, I think, in the media by colleagues and so forth. Would you advise people to get into government or to serve the country in such a way, or would you have reservations?
Yeah, you cite some high-profile cases, but I know many scientists who work either as federal employees or as in the national laboratories, and they are as dedicated and as honest as people in academia, you or I, would be. We'd recognize them as credible scientists. The problem is when that work starts to touch policy issues. And whether it's epidemiology or it's climate and energy, other environmental issues, that's where sometimes people will spin the story and not give a straight answer. I'm far enough along in my career. I've got enough of a reputation. I frankly don't care. My main goal is to just try to inform people in a transparent, unbiased way.
And I guess lastly, now with the advent of artificial intelligence, large language models, and so forth, I found it very exciting, actually, and I'm playing around with it not only as a, human interest level of just, constructing my own, what I call bribot, but also constructing physics tools, because I do believe that we are stuck in a model that's 1,000 years old, and how many 1,000-year-old things have not been disrupted? And I do believe we could have things where we have distance learning, we have artificial Galileo I've worked on, because I have access to the written text of the dialogue, which I've recorded the first ever audiobook ever by Galileo with Frank Wilczek and colleagues at Carlo Rovelli and others. But when I think about the potential for that, so here at UCSD we had famous Herb York, who I'm sure you knew, who plays maybe a millisecond role in Oppenheimer. We had Harold Urey, who is a big component of the Manhattan Project. We had all these people that were involved in government and also in organizations. But the question I have is, how do we translate whether or not this is an existential threat, an existential benefit, a boost to society or not? Where are you falling in this camp of, can artificial intelligence lead to, say, new laws of physics, perhaps?
Well, we've seen it lead to new strategies in Go, for example, right? And you take an AI that's learned how to play Go, and it surprises the masters, right?
That's right.
It did it that way. My God, I never thought about that, right? So I think there are specialized AIs we can be building. Physics is a great example, or even something more narrow in general relativity, for example, that would be tremendous tools for education, for research. I mean, even now, of course, I'm sure you and others find, as I do, Google just a wonderful way of ferreting out information that you need or are interested in. So I think the AI, ChatGPT, for example, will be, when properly tuned, wonderful. I'll give you my experience with ChatGPT, all right? And one of the things I'm interested in is Greenland's ice loss, right? And so I asked it, this was a couple months ago, is Greenland losing ice? And I get kind of the standard media story. And then I said, well, what about this paper that shows, in fact, it's not losing ice so rapidly? And it took me about 4 iterations until I got to something that was consistent.
Yes, you have to supervise
research. Yeah, you've got to keep correcting it. But I think it's got a lot of potential. So I'm not worried about an existential threat. I think it will be a great boon.
Well, Steve Koonin, professor, I think of you as an educator, as a curious soul, as somebody who's very much interested in solving the biggest problems, whether it's at the realm of the smallest possible entities, nuclei and quantum fields, all the way up to entire planetary scale phenomena. I want to thank you for spending so much of your valuable time here with our humble podcast, and I know our audience is forever grateful.
It was a great conversation.
Thank you so much, Steve.